Hello. Thank you. Thank you for the introduction, Trish. My screen is shared on the presentation, right?
Yes.
Yes. Okay. Thank you. So yes, so today I'd like to talk about our work on smart city construction and living. I'm from the Chinese University of Hong Kong, so it's evening time here. The research focus of our lab is on the dynamics and control, developing robot mechanisms and controlling them for a range of applications in biorobotics, in architecture and construction, which is very demanding in Hong Kong, and service and maintenance. So in Hong Kong, the robotics can really help the aging and lack of skilled workers. I guess it's also another country, but in Hong Kong particularly, so many high-rise buildings, so many housing demands, and there's so much work that we need to do, from building stuff, maintaining them, infrastructure, civil works, and even into the house after it's built, right? So there's a whole range of tasks that needs to be done. And there's a lot of common challenges faced, which I think, we need smart machines in order to solve it. So this could include the design, how to design this in a smart way, design the systems mechanically, the sensors and signals in the system, making intelligent decisions, and also integrating this to a proper workflow so it's actually useful in operation. So today I'm just going to highlight a few applications and a few examples of the work that we do to show the need of this. So usually there's two approaches currently being, a few things I want to discuss. One is, do we mimic human workers task by task, or do we invent new robotic processes to do the whole thing in a new way, in a new thinking? And also, do we want fully autonomous robots or human-assisted robots? So here's some background. Here's some example projects that we've been doing. So one is constructing brick structures. You can see through a range of exhibitions and demonstrations, we use robots or cable-driven robots in order to pick and place bricks. So cable-driven robots that have large span, good payload to weight ratio, and easy to set up in principle, and also bio-inspired in nature. So this is an example at the Hong Kong Science Museum. So we ran this exhibit for about a year and a bit just to show how the robot system works. You can see a time lapse of the cable robot, picking and placing bricks from an arm deliverer, and it builds the structure. I'll talk more about the intelligence behind it required. Another example is a site project that we're currently developing on campus to build a permanent brick structure. This is an interdisciplinary team with School of Architecture. So we have a cable-driven robot that could reconfigure its cable attachment points to avoid the structure, and also a whole robot arm delivery system to deliver bricks from pallet or setup to the robot. So there's a little current progress demonstration where we are. So you see the robot could pick up the bricks and pass it along. This is the more traditional, boring stuff in some sense, and then passes it to the cable robot, which then picks it and places it in the large zone. So about 10 meters by 10 meters. So I think it's showing the real application setting for this type of robots, even if it's a little bit small. So one of the things I want to talk about is the interplay between the architects and the engineers. So, which comes first? Should the engineers design the robot first and the architects build what the robot can build? Or architects design the building first and the robot engineers or roboticists try to solve the problem? Of course, we know, at least from the community here, who is more important. But how do we do this in a seamless way, right? Should it be automated, or should it be human involvement? Because design is human involvement, right? So that we sort of proposed a workflow where we have a design of the robot and design of the structure. So it's sort of in three stages. We have a heuristic robot design library that generates a whole bunch of different designs, showing all of the properties like force, capabilities, workspace, dexterity, cost of the robot even, and the efficiency and all of that. And that would generate a lot of options. Then the architects and the engineers sit down and discuss what should be done from both perspectives to choose a zone that they will build. Once the zone, in other words, the colored region in the pictures are set, you choose one of them, then they will do computational design that automatically populate with bricks on different designs, generate all sorts of funky designs that then they choose again, to see that's the final design. So sort of a workflow to get everyone working together. An interesting little sidestep from this project is, we want to look at frames that are not rigid. So typically we have these heavy frames. You see in the previous picture here, these massive pole frames that are very strong, and because you don't want any bending, you don't want the system to bend. The question is, what if you let it bend? What if you purposely let the system do some bending? And if you purposely do that, you have to naturally solve a problem of the dynamics of the bending, right? How to model the bending, how to get it accurate. So we had to, we started, you see in the picture on the right, the robot when it's just assumed to be rigid, so it's very erroneous. And then we put a bending model inside, and right now we're also doing work with iterative learning control that it updates itself, slowly over time. So that's one of the examples. Another project is a facade robot, robot that acts on facades of high-rise buildings, doing painting and window cleaning, for example. So there's an example with the cable robot hack. Instead of being operating by itself, it carries a robot arm. Sorry. And then it approaches the glass surface and it will apply contact, using the force sensing. That's a traditional control. And we are also applying, iterative control techniques to improve its performance over time with these sort of systems, because these are a hybrid and relatively redundant system. We could also do painting. Another example of this sort of robot in a different, it's a different embodiment, I'd say, is a robot to do tapping on the facade. So rather than using vision, it's using physical hammer tapping. That's what's traditionally used for concrete and tiles in Hong Kong. So we have a robot that lowers, it's like a suspending abseiling robot. It lowers the end tool on the facade. And then we've done this on actually 2 different site trials to see the data. And we've got a mobile base on top, so it's not mounted rigidly to the building. It's actually something lightweight and mobile, and it's just going to move around left and right, in and out to do this. And there's a range of challenges we need to solve, and still solving, I'd say. We want to develop ultimately a robot that abseils down the surface. It bounces and slides on the surface like abseiling down rocks to go down, and then as it goes down, it will put in contact, jump off again, and balance. We also need to be able to localize all of this and integrate with the workflow, integrate with the building information model. Also mapping data and intelligent health prediction. These are all stuff that we need to be solving. What last bit that links a lot of this work together is I want to talk about is actually teleoperation. So rather than a fully autonomous mode, which is hard in buildings in practice, you could also have a teleoperation mode, because not all the time, you just want to remove the person from the work. In the risk work, you don't want to remove the person out of the loop. So by having in some sense, would this embodied intelligence be the human actually there? But you don't want the human just blindly teleoperating. So just like in surgery, you want to have a cooperation, both of them working together. So we did a range of works on this. So first one is a work on a teleoperation device. This is for robots operating in large scale. So typically you would have one device if you're doing just like a robot arm control. Here we have 2 devices because we want operating in larger space. So we have this macro micro control scheme. So actually here you see the joystick is doing high speed control. So it's doing a position to velocity mapping, high speed control to move the robot. But once you're a bit closer, if the high speed control joystick would have lack of resolution. So you want to use fine tuning using the trackball. Okay. So then then you need to also deal with the problem of control authority. You need to shift between which device to use, depending on who's giving more effort, who wants to dominate. Because you're working on the same agent, the human is doing it, one will dominate. So we show the results, we see the error and the error actually it should be error and the other one should be time, but you see a similar result where error and time, basically it diminishes when you have a dual interface device. And then another one, this is actually a work we're also collaborating with Etienne, who presented earlier, is to do intention estimation. So if you had 10 targets that the robot knows, but the robot doesn't know which target the human wants to go to, it doesn't know the obstacle, how can it use the force torque sensor to guess what's happening? So it's a predictive controller. We need to estimate the human's target, what they want to do. We need to switch the roles. When the human wants to dominate, let them dominate because you're doing something maybe not right. When the robot wants to dominate and the human thinks it's okay, let the robot dominate and be more accurate. And then, we want smooth motion of the robot so the human could guess the robot's intention. So this is a human experiment we did with 8 subjects where the top is without assistance, the bottom is with assistance. And you could actually get much quicker results. You can see the error is much less when you do so. And the forces required in the joystick is much less, and the time is much less. One last thing I want to quickly talk about, a little bit of augmentation on humans, because we want to use this on people who need prosthetics. We also want to use this on, let's say, building construction, is devices that you could swap in and out. So this is a more philosophical question I want to end on. Do we want one intelligent device, like a full robotic hand that could do everything, like a human hand? Or do we want multiple devices that are dumb? Every device is dumb, but the combination of them maybe is smarter. So here you can see we have different tools doing different stuff. The user just switches the tool in and out, and they could do different things, from cooking to playing the violin, and even rope skipping, all sorts of tasks. So here we're designing these tools. We want to design it intelligently. We want to use input as the shoulder motion, the output as the motion they want to produce for a task. Could I automatically design the tool position and tool orientation and the shoulder motion without having to do this manually by trial and error, like what we do normally? Can we do this as an optimization problem? And then how do the humans react to the tools? And the last problem would be, right now there are passive tools. Could they also be active tools? So I think this is a different approach to thinking about one size fits all, or many things that you could just interchange, but each is specific for one purpose. So finally, thank you to my team and also all my collaborators for all the hard work, especially during the pandemic. So thank you, and sorry I'm maybe 2 minutes over. So thank you.